All right, there we go. So I'll go ahead and get started. It's a pretty cozy group, so if you have any questions, feel free to give me a shout out. So I'm Mark Astley. In game, I go by Salacious Necrosis, and on the forums, I post under that name as well. What I'm going to talk about today are developing third-party apps on Google App Engine, and in particular, I'm going to focus on apps with a need for scalability. So the the application that I'm going to use to demo here is one that I wrote called EveKit. Turns out that was a really bad name. If you Google that, it's some sort of antifungal drug. I didn't know that when I chose the name. But anyway, what EveKit does is it does what most third-party apps do. It uses a library to download XML data and uses the static data export and so on. It does a couple of specific things with it. The first thing it does is it lets users define accounts, so you put in your key and your vcode, and then it goes and downloads all of your data as frequently as the API allows, so that's about every 10 to 15 minutes or so. And then it saves all your history, so all your wallets, your kills, your mail, your market orders, whatever, it saves everything. And then it turns around and has an API on the front end to give you access to all that data, so you can access all of your complete history and your API data. It also has entry points for the static data exports, the references, so skill tree and things like that. And then every night it copies all of your data into spreadsheets, and you can get your data in bulk form if you want. So what are the scalability needs of an application like this? Well, on the back end, so we're syncing a lot of data. Last weekend when I looked, we were doing about 6,000 syncs a day. So that was over about 80 accounts. Obviously, the more users we add, the more load there would be. So there could be pretty high network and storage load over time. And this is something that we want people to be able to depend on. So it kind of needs to be redundant. It shouldn't just fall apart if one of the processes doing the syncs dies. It should just kind of restart so that you get a regular stream of data here. But on the back end, the nice thing about that load is it's fairly predictable. We can tell from the number of accounts and how frequently we're syncing what sort of load we can sort of expect. The front end is a more typical web type load. So there's potential for high traffic, but it's not necessarily something you can predict. If the site gets really popular one day, there could be a flood of requests, and other days it might be totally dead. So the scaling you need here is what they call elastic, meaning you want to be able to detect when there's lots of traffic and scale up and add more processes to handle the traffic, and then scale back down again when everything goes away. And of course, you still want redundancy. You want the site to be generally accessible. It's a disaster if somebody's trying to go to the site and can't get to it. So this app has the potential for large scale. And so what I'm going to talk about mostly is how I decided to address this with EveKit using Google App Engine. So just looking at this app, by the way, you can certainly do this all yourself. Many developers have implemented this sort of thing. But one thing I noticed when I was looking at this is that a lot of cloud platforms are specifically targeting this type of app. So this is a very standard internet-style app where there's some unpredictable load or whatever, and there's lots of systems out there that are designed to handle this sort of thing. And so I basically decided to give one of those a try instead of doing it myself. So the observation is that cloud platforms are kind of targeting this space. So hey, let's try that instead of rolling your own here. So I decided to use Google App Engine. That is a platform as a service specifically for web applications. It's integrated with all the other Google offerings, so the general Google Compute Engine suite, and that includes other things like Cloud SQL, so you have those options as well. The main features with App Engine are it has 4 main languages that it supports: Java, Python, Go, and PHP. And you can now support other languages, so Node.js is very popular. You can do that with something called a managed VM. Scaling, that is handling load, can be manual or automatic, depending on what you want to do. And it has one nice feature: it has a built-in, highly scalable NoSQL store, which I'll talk about a little as well. Now, a little bit of full disclosure here. So I was working at Google when I started working on this, which is also kind of why I chose Google App Engine, but I'm not trying to be a shill for Google. You can do the exact same thing I'm describing here on Amazon with Elastic Beanstalk, and there's other offerings, Heroku and things like that. I also want to provide a little bit of a cautionary tale here. So that's just showing what EveKit does in terms of using App Engine. So there's a lot of misconceptions about using cloud, and it applies to things like App Engine as well. A lot of people think to do this because they think it's cheaper. If you are doing anything non-trivial, you'll quickly find that's not really true. So I'm not really trying to save money here. That's not the goal. I mean, I don't want to waste money either, but really the benefit here is time to market and agility. The other thing, the other misnomer is a lot of people think this is easier. It is in some sense, but it's better to say that it has some unique challenges. So you're going to have to think a little bit differently when you develop an application for something like App Engine than you would if you were standing up your own servers on your own hosting solution. So those are just some anti-patterns to be aware of. Okay. So what goes into a Google App Engine application? So the four things on the top there, those are the main things that you tend to use in a Google App Engine application. There's a set of modules. That's where your code actually lives. So it's all of your code that's handling web requests and so on. On the upper right, that's my icon for representing the DataStore. That's a pretty standard NoSQL data store. It has some fancy features, which I'll talk about a little bit later. But if you're familiar with the space and you know about things like Mongo and so on, you'll recognize DataStore pretty easily. The task queue is a way to handle dispatch and do certain common patterns in distributed computing, like distributed workers and so on. It's just a place to put requests until it's time to dispatch them. And you can also implement things like cron jobs using that. And then Memcache, if you know what Memcache-D is, Memcache is basically Google's versions of that. It's just a way to store things, not quite in memory, but with similar latency, and make it accessible to a bunch of modules running in a distributed environment. The bottom two things here, Cloud SQL and Cloud Storage. So Cloud SQL is essentially MySQL in a cloud environment. They use exactly the same API as MySQL, and you tune it the same way, pretty much. The only difference is they're doing some tricks around CPU scheduling and co-location and so on. So it's not like it's really your own instances running on dedicated machines. And then cloud storage, that's Google's competitor for S3. So if you're familiar with Amazon S3 at all, cloud storage is basically a block store or a blob store or object store. It's a place to put files. It's append only. It's not quite a file system. Okay, so how do you program in App Engine? Well, there's two basic things you do. First of all, you write a bunch of modules, and they are what handles your actual web requests. So if you're using Java, for example, you implement an HTTP servlet, and you implement the do-get method. And then requests can have time bounds, and basically depends on what sort of instance you're willing to pay for. So the free or cheap instances, you have 60 seconds to handle a request, and then your application goes away. And if you take too long, they will kill the request, and you'll get an exception. If you're willing to pay a little bit more, you can have unlimited requests, so you can sit there and spin all day long if you want to. So you write a bunch of modules, and then you glue them together with task queues. So task queues are a way to provide dispatch and resiliency, and as I said before, it's a way to implement the distributed workers pattern. So the idea is you want to do something periodically. You drop something into a queue and you give it a particular execution time, and then at that time it fires and gets dispatched to one of your modules, and then you do whatever you need to do. And then the way you do resiliency or sort of error handling is any non-OK response, so 200 is the web code, HTTP code for OK, any non-200 response causes the task to be requeued automatically. So if you take too long or otherwise your process dies, the task will go back in the queue and get dispatched again, possibly to another worker or the same one when it restarts or whatever. You can also define limits on your queues, rate limits and burst controls, so that if you make a mistake or something like that, you won't flood the system. If you're really technically inclined, what they're implementing is a leaky token bucket. So if you want to geek out, you can look that up. So this is the basic programming model. It's pretty simple. You just have to fit whatever you're doing now in sort of a standard setting into this sort of model. It's a very similar or typical distributed programming model. So let's take a look at what EveKit looks like in this sort of world. So with EveKit, we've divided the two logical things that EveKit does into a backend and a front end. So the backend is where we actually do all the syncing, and on the right here we've got the good old Eve XML API. And the front ends are where we handle all of the web requests, and then we're storing all of the sync data into the data store, And I have a memcache there to speed up some things, which I'll show you shortly. The static data export I've dumped into a Cloud SQL instance, which is pretty easy thanks to Steve's exports. And then cloud storage, I'll show you what I'm using that for in just a second. So a typical request on the back end works something like this. So the first thing we do is we have a task that does a dispatch every time it's time to synchronize somebody's account. So right now, like I said, we do this every 10 or 15 minutes. So I just have a cron job running basically. The backend picks up the request. It looks like a web request. And then we go and we hit the XML APIs, and we do it for whatever the key says we can do, and we handle errors and so on. And then with all the data that we get, we drop it into the cache, but we go through memcache and then into the data store. So what we're doing here is we're checking to make sure that the data has actually changed. So if you've looked at any of the API data before, you'll notice that a lot of the data doesn't change very fast. And for like wallet queries, for example, most of the time you've seen most of the queries already. So we use the cache to filter those things out so that we only write things to the data store that actually are worth writing. And so we do an update there from the backends. And then finally, once a day, we do a scan over all of the data in the data store, and we dump it as a bunch of spreadsheets into cloud storage as a big object. So I said before that the scaling here is fairly predictable just based on the number of accounts we have. And so for scaling, what I do is I do manual scaling. So I just have basically a variable I change, and that changes how many backends I need to run. On the front end, the way things work is we get a bunch of web client requests. So these could be actual browsers. They could be anything that's capable of setting a web request. Could be curl or whatever. And then all kinds of things happen behind that. So if somebody's looking for actual API data, we go through the memcache and go to the data store potentially, depending on if we have the data or not. If you want static data exports, then we're going to Cloud SQL to pull it out. And if you're looking for your dump, we get it from the dump request. If you're looking for reference data, we actually go all the way to the XML API, and then we cache the results. So the latest skill tree or whatever, we cache those with whatever cache timer they've set. So as I said before, the front end here, the requests are unpredictable. It's based on I guess how popular the site is on a given day. And so in this case, we choose to auto scale based on the load. And so the way that works is when a request comes into the site, App Engine keeps track of how long that request has been waiting. And if that exceeds a certain threshold, it'll kick off another front end. So it tries to bound how long any particular request has to wait up to some max. So I've set it to some sane value so I don't have hundreds of these things started up. But that's essentially how the whole thing works. Okay. So I said before we had scale requirements and redundancy requirements. Basically, I want to be able to scale to handle the load, and I want to be redundant so that the service is something you can actually rely on. So how do I actually meet those requirements in Google App Engine? So let's talk about the back end first. So we get redundancy in the back end through a combination of elasticity. That means being able to add more nodes as needed. Atomicity, which means consistently changing data in the face of failures and so on, and retries. So essentially, I rely on App Engine to ensure that there's a minimum number of back-end modules running. I tell it how many need to be running at any time, and it monitors for failures and restarts as needed. Memcache and DataStore together is how I get atomicity. So for memcache, there is an operation called update if not changed. So that lets me safely process updates. You can imagine you might have multiple backends trying to hit the same data. I can use this feature to make sure that only one of them actually does a change. And then DataStore supports transactions, so I can make sure I at least order my changes to the DataStore and not end up corrupting anything. And then finally, I use task queues to retry and requeue on failure. So using the features I said before, where if we have some massive failure, all of the tasks won't just disappear. They'll end up back into the task queue, and we can retry them again. For the front end, basically, I'm relying on the auto-scale features that I described earlier. So the front end has the virtue that it's basically stateless, and so it's pretty easy to auto-scale. I just need to tell App Engine how much latency to tolerate before starting up a new module, and it does it for me. So from these particular features, it's pretty easy to guarantee scale and redundancy, but a pretty natural question to ask is, what about performance? I mean, it's great if you can sort of rely on the site, but People will get pretty tired of this if the performance is awful and you can't get your data. And it turns out that, at least in this particular application and most of the other ones I've done on App Engine, this is really impacted by storage. If you make a bad choice around storage, you're not going to be very, very happy with what you get. So the first time I wrote EveKit, I actually put everything into SQL. I stored all of the sync data as tables into SQL using Cloud SQL and ran everything from that, all the state and so on. And it was pretty bad. So the table on the middle column here under Cloud SQL, these are the stats for doing a sync of an account. I had about 30 accounts at the time, and I was doing a sync every 20 minutes. So on average, it took about 4.5 minutes to do sync processing. And when things got really ugly, it took well over an hour to sync a single account, which is pretty bad. And all the other stats look pretty bad as well. And so when I did some profiling here, what I found was there's tons of lock contention. So if you try and do sort of the natural thing here, you would tend to make a table for each type of API data. So you'd have a table with all the wallet transactions in it. You'd have a table with all the kills in it and so on. And when you do that, you end up building in a lot of lock contention. So you have to kind of do strange things if you want to get around that. The other thing I found was there wasn't enough CPU for SQL itself. So when you create a Cloud SQL instance, you have to tell it how big of a machine or how much of a share to give it. And unless you went up to close to giving it a full dedicated machine, you couldn't really get enough CPU to get performance. And at those levels, it's definitely much cheaper just to, in fact, run your own SQL machine. You're better off doing that in terms of cost because the cost gets very prohibitive. So that was kind of depressing. So what I decided to do was port the API sync side of this to DataStore, and the table on the right shows the results of that. So it's an order of magnitude better. We went from 4.5 minutes to 43 seconds on average for syncing an account. And in the worst case, we had about 6 minutes. Now, it's still true that if you have some massive corporation and you put your key into EveKit for the first time, it's going to take a little while. It'll probably take a couple of cycles before we get all your data. But once you get it all in there and we start getting into a regular clip and the caches get warmed up, you're not going to see anything worse than 6 minutes, which is pretty good. And so the reason here is that the way that the DataStore does locking allows a lot more parallelism. So if you're careful with how you structure your data, you can do a lot better, and it's a lot more natural than doing it the way you would do it in SQL. In the end, I think I decided I would have to make at least a table, if not a whole database instance per account to really get the locking that I would need in SQL, and so I didn't want to do that. So why is the DataStore faster? So I'll explain a little bit about the model and where the locking comes in. So in the DataStore stores things called entities. Every entity has a kind, which is just the name of a type. So in my example here, my kind is car. Every entity has a unique ID. It's unique for all of the entities of the same kind. So in this case, the ID is 123. It can be a string or a number. It doesn't really matter. And then entities have properties, and in DataStore, these are the usual Java properties, so strings, ints, doubles, dates, things like that. Then also every entity has a unique key, which is just the kind plus the ID, and so that's that green text up there. And then what you can do is you can link entities together in a hierarchy, in an object-oriented sense. So you can make an engine, for example, that's linked to a car, and you link it by making a parent relationship, and the parent is just the key of the parent to the entity. It still has an ID that's unique among all of the entities with the same name, and it can have its own properties. So in this case, I put a displacement as the property. And then the key for the sub-entity here is the name of the parent, so car123, plus the kind and the ID for the sub-entity. And then what DataStore does is it organizes everything in this hierarchy into something called an entity group, where everything has a common ancestor called the root entity. And so what they do then is they use this model to define the granularity for things like transactions and consistency. So some of the features on the DataStore, all transactions are on entity groups. They're not across entity groups. And so essentially what you get is strong consistency within an entity group. So if you run a transaction over an entity group and you change one of the elements, it's immediately visible to anybody who's doing the read after your transaction commits. And what that does is it gives you a way to reduce lock granularity. Between entity groups, that is, if you have two separate entity groups, it's eventually consistent. So when you do a read after a transaction, it may take a while before you see the actual latest data. And then there's a few other nice features. DataStore has SQL-like queries. They're not quite the same. You can't do joins or anything fancy like that. And it also allows you to define indexes on properties that you want to search for faster queries. You can search for anything you want, but if you don't do an index, you have to do a scan, which is pretty painful. So essentially, in EveKit, what we did is we took advantage of entity groups, and we put each account in its own entity group. So now when I'm syncing two different accounts, they're not going to collide with each other at all in terms of lock contention. And they were when I was doing this in SQL, so it was pretty bad. And then I defined indexes on things that I'm likely to want to query a lot. So think of item IDs and ref IDs in the wallet and dates for just about everything and so on. So this is essentially why you can make DataStore go much faster than SQL. You have a lot more control over the granularity and locking. And then if you throw a little bit of caching in front of this, you can really make it fly. You can make it go a lot faster. So what we've done here is I've basically put a cache between the modules in the data store, and it's a write-through cache. So if I don't change the data very often, I'm going to get an immediate response from the cache. And when I do need to change it, I can just write through. And so there's a real nice library in that's open source that works very well with this called Objectify. It's essentially a wrapper around the data store that implements a write-through cache, and it happens to be written for Java. It also lets you write your entities as plain old Java objects. I didn't go into what these things really look like if you use the native API. They're pretty gorpy. This is much easier. And you just basically annotate your Java objects. So if you're familiar with this space at all, it's similar to Java data objects or Java persistent architecture, things like that. It supports inheritance and all the usual object-oriented stuff. So it's a pretty natural model. And finally, they have simple wrappers for transactions as well. So it's pretty easy to write those things. So a little bit of code. I was afraid I was going to be the only guy that showed actually code on a slide, but Steve bailed me out with his code. So I only have one slide of code here. Just to give you an idea of what it actually looks like when you do it. So on the left is the base class for all of the API data that I store, anything that I sync. And on the right is an example for a wallet. The base class, it's labeled as an entity so that we know it's a data store entity. It references the account, so that's the root entity for this particular entity group. And then it has an ID, and the IDs for everything are stored in the base class. And then on the right, what we do, if we want a particular type of data, for example, we subclass. So technical detail, the entity that's actually stored in the data store is still called cache data, but Objectify does some magic so that when we pull this thing out, it's actually instantiated as a subclass. We define a bunch of indexes on things we're interested in, so the account key, and this is a wallet, right? So you want to look at date a lot and so on. And then one interesting thing you can do here is if you want to store a type that isn't supported by the data store, like big decimal, for example, then you can just serialize it and store it that way. So for wallets, I chose to use fixed point representation rather than floating point, so I guess I'm really anal that way. And I can store it still in the data store because I can serialize it here. So that's what the code looks like. Okay. So I do have to talk a little bit about cost because if you go down this road with something like App Engine, you should at least know what you're getting into in terms of paying for the thing. So essentially the philosophy, at least with App Engine, and it's true in a lot of other clouds, is the fixed resources are really cheap, meaning storage and anything they can just put on a disk somewhere. Where they really charge you for is the back-end instances or the front-end instances and operations on the API. So those are the things to optimize. So in the case of EveKit, the big ticket items are the data store ops and the back-end modules themselves. So those two things together, that's 75% of my cost every month. There's just the reads and running the back-end services. The actual storage, gigabytes on a disk, that's 3%. It's noise, really. I should be storing a lot more potentially than I am. And the data store reads alone, that's almost half the cost. So that's 47%. So a natural question is, can we do better? Am I doing as much as I can? And the answer is no, not really. It turns out that key-only queries on the data store are free. So what that means is you can do some massive query or whatever, but as long as the answer that you get back is only the set of keys that match that query, it's completely free. It's only when you want to get the actual data that you have to pay. So it's good for doing existence checks or something like that. And the other thing to observe is that writes are pretty rare with API data. If you ever look at your data, you'll see that the character sheet doesn't change a heck of a lot over time. And even things like assets, some people have thousands of assets. Most of them probably don't change very much. And so you should be able to take advantage of that. So I did that. I added some caching, and I converted some of my reads to key only. And let's take a look at the results here. So what I did was I set up a dedicated mem cache that's no bigger than 1 gigabyte. So that's the most I can cache. And there's a cap of 10,000 ops per second on the mem cache. And once I did that, I got about a 60% cache hit ratio, and I ended up using about a little more than 10% of that. So I've got plenty of room to grow more there. And I added some specialized caches for wallets and assets and kills and standings. And if you know about these things, you know that wallet, when you retrieve it, most of the entries that you get, you've already seen before because you get a month at a time. And like I said, assets change relatively slowly and so on. So these are good targets to cache. And so when I did that, full reads dropped from 6 million a day to 4 million a day. So it was worth a third improvement right away, which is pretty good. There is a natural limit because I do this bulk dump every day. When I looked last weekend, I still need to do at least 1.2 million reads a day just to go through all the data and dump it. So that's sort of the theoretical limit. But I'm still pretty far away from that. So there's a lot more I can do. In particular, I need to tune the time to live on the cache. I'm probably expiring some data way more quickly than I need to. And there's lots more queries I should move to key only since, hey, those are free. So it's totally worth doing that. Okay, so it works. So this is kind of an aside now. What's next for something like EveKit, and how will it affect my use of App Engine? So the first thing I want to do, the whole goal of EveKit is trying to be a platform for other people to develop their own third-party apps. The problem it's trying to solve is every time somebody goes and wants to write their own third-party app, the first thing they do is they go and look for whose library should I use to pull the data. They pull one of Steve's dumps, and they figure out a place to put it, and so on. And so I'm trying to short-circuit all of that by giving you an easy way to get all your data. And so I've sort of done the first part, and now I want people to use this thing to build their own apps. So I think the way to do that is something called embedded apps. And so the idea is give people a way to write their own apps against this API, let people using EveKit select some of those apps and have a safe way to sort of bridge their data over to those apps and do interesting things with it from it, and ultimately build sort of an ecosystem around this. So that's sort of the long-term goal, and even the even longer-term goal is to give non-devs a way to build their own apps. Right now, it's a pretty steep learning curve. Even if you know how to develop, there's a lot going on that you sort of need to learn to get going, and there seems to be some demand here. I'm not really sure about that, but maybe there's some space here. So this won't really change EveKit a heck of a lot, but what might change it more is this idea I have called the Eve Wayback Machine. So this is very much like the Internet Time Machine type of idea. So I'm already getting a bunch of data. The idea is, what if I just version it? So yeah, I'm keeping your history of wallet, but what if I kept a history of all of your assets, or every time your character sheet changes, I keep a history of that, and so on, so that you could go back at any point in time and look at how things looked 6 months ago or whatever. So that will definitely affect what I'm doing in App Engine. I'll have to write a lot more to the data store and version some things differently. And I thought, I was thinking about all the places that locations are stored in the data right now. If you run a corporation, you have location information for your members at various times and so on. And so there's probably some pretty interesting things you can do if you were looking at, a time lapse of the locations of all the members in your corp. That's kind of interesting data. So that's something I wanted to work on as well. Okay, so just to recap briefly, it was pretty easy to get scale out, or basically an event-driven load, up on App Engine. I had to do some tuning and so on. If there's one thing to take away from all of this, be careful if you decide to use a Cloud SQL-like application. If you're doing something that's read-only or has low lock contention, it works pretty well. If you're doing heavy write loads, not so much. And this is also true in many ways for Amazon as well. I tried their version of Cloud SQL and essentially had the same results. The data store is efficient, but you can spend a lot of money if you don't spend some time tuning. For a load like EveKit is processing, caching is definitely your friend. The API is very cacheable, I think. And this was pretty easy for me with objectifying the Java layer. And it's definitely worth your time to optimize for the free reads tier. So I'm planning to continue the investment here in EveKit for the next features, so I don't think it's going away anytime soon. I'm happy to take requests for other features as well. I did put out a survey, and I got exactly one response, so whoever did that, thanks. I appreciate the one response. And that's it. Thanks a lot. Any questions? Yep, go ahead.
Yeah, so you talked about kind of the performance benefits that you picked up from going from cloud to DataStore. What are the cost implications, and why does the SDE still sit in the cloud SQL?
So I'll answer so the question was why, what were the cost impacts of going from Cloud SQL to DataStore, and the second part of the question was why is the SDE still in Cloud SQL? So to answer the second question first, because I'm lazy, Steve has made it incredibly easy to just take the data and dump it in. So you could, in theory, use SQLite. He's got a dump in SQLite, but the problem with App Engine is it doesn't really give you write access to the local file system, so I can't use SQLite. So I thought of doing that. The other way to do it, it's the data doesn't change at all. You should really just put it in your code in some way if you can, as tables or whatever. But I haven't got around to that yet. To answer your first question, so cost went up quite a bit going to DataStore. The Cloud SQL offering, depending on how you charge, you decide to pay for it. You can either pay for it per use, or you can pay for it as sort of a lump sum daily fee, and it's pretty affordable. But what I found was to get performance out of it, I would have to pay for essentially a full instance with lots of CPU and memory and so on. And then it was not such a great deal after all, and would be hard to tune. That's what I found. So DataStore, it's more expensive right now, but I have at least a lever I can push on and try and tune it better. Whereas Cloud SQL, there's only so much you can do at some point.
And so at that point in time, if you're going to embed SDE, wouldn't that affect kind of your request timing?
It depends on how I embedded it. If I was really sharp, then I would put the SDE into its own modules so that it doesn't interfere with anything. Essentially, you could think of them as arrays that you could just embed in code or in a table or something like that, something you'd read locally in cache. I could put it in its own modules and not really have to worry about it. I could even put it in static sheets if I wanted to and have some way to select out of it. So I don't think it's going to affect anything when I get around to doing that. Yep. Any other questions? Okay, thanks a lot. So I'm on the forums quite a bit. If you have questions about this or API stuff in general, I'm pretty happy to answer those things. And thanks a lot.